Welcome back, students. In this video, we're going to talk about bond enthalpies. So we know that what bonds are. They're the chemical bonds, covalent bonds, and enthalpies are heat energy, right? So we're going to talk about basically how much energy is in a bond. Fundamentally, that means how much energy does it take to break a certain bond that is then has to be put into the bond to get it to break. And if a bond is broken in a chemical reaction, then how much energy is going to be given off by that bond breaking. So when you form bonds, the species become more stable and they release energy. So bond formation is then an exothermic process when you form bonds. When you break bonds, you have to put energy into bonds to break them. So energy has to go into them for that process. So breaking a bond is an endothermic process, okay? And very often in chemical reactions, you have some bonds breaking and new bonds forming, right? And both of those things will happen in a chemical process, in a chemical reaction. So let's talk a little bit more about what bond enthalpies, how we use this to calculate the delta H of a reaction. Remember that this is our fourth method of calculating an enthalpy change for reaction. We're going to use bond enthalpies. So again, covalent bonds form because when they do so, energy is released. Remember, this is exothermic. And the overall system drops to a lower, more stable energy level. In contrast, it actually requires an input of energy to break a covalent bond. So when bonds form, they release energy. When you break a bond, it requires energy to go into the system. So this bond energy that you have to either input to break the bond or that is released when a bond is broken is also called the bond energy or the bond enthalpy. Basically, it's the enthalpy, the heat energy of that bond, because the bonds can give off heat energy when they are formed or take in heat energy to break them. Now, one of the ways that we can use this is that bond energy, the enthalpy for a bond, is roughly the same if it is a bond between two of the same type of atoms in the same bond order. So let me explain what I mean by that. Bond order means whether it's a single, double, or triple bond. And if it's the bond between the two of the same type of atoms, then it doesn't matter where you find that type of bond, in one molecule or another molecule, they're going to have approximately the same bond enthalpy. So for example, we can consider the bond enthalpy of a carbon-carbon single bond in a variety of molecular environments, and then take the average. Of all of those bond enthalpies that we find for carbon-carbon single bonds, everywhere we find them, and that will give us a close approximation of what any particular single bond CC, carbon-carbon single bond enthalpy will be. And so that's what we have here in our chart, in our table. We have average bond enthalpies. So we have them for single bonds and double bonds, and we can have them for triple bonds. We can have them for a variety of elements that are bonded. One thing I will point out, there is one case where we have to be particularly careful about where we find the type of bond, and it's a carbon-oxygen double bond. The average usually for that type of bond is about 745 kilojoules per mole of those bonds that we break. But carbon dioxide has carbon-oxygen double bonds that require considerably more energy to break. And so we have a special entry for the carbon-oxygen double bond when it is encountered in a CO2 molecule. Okay? All right, so how does this help us? Well, to calculate the delta H of a reaction, remember that enthalpy change for a reaction, using bond enthalpies, we first determine which bonds of which type are being broken in the reactants of the reaction. So broken in the reactants, we're breaking bonds in the reactants. And then which new bonds are being formed in the products. So you're going to have to input energy to break reactant bonds, and then you get out some energy that's released back to you when new bonds form in the products. And it will be very helpful to see if you draw Lewis structures. So Lewis structures are very helpful to enable us to see what kind of bonds are involved, which ones are being broken, which ones are being formed. We can then calculate the change in enthalpy for the whole reaction by just adding up all the bond enthalpies for all the bonds that were broken in the reactants minus the sum of all the bonds formed in the products. So now we've got an equation, and I'll draw your attention again to the back of our periodic table where we have an equation list, and you will find this equation right here. Delta H0 for a reaction is the bond enthalpies for the reactants, the sum of all the bond enthalpies for the reactant bonds minus the sum of all the bond enthalpies for the product bonds. You can include all of the bonds in all of the reactants and all of the bonds in all of the products, but it makes our math easier if we just look at the bonds that are broken. Because in some cases, many bonds might not be broken. And then for the products, you can just look at the new bonds that are being formed. But the math will work either way. Bond enthalpies for the reactants minus bond enthalpies for the products. Okay? So, it's the sum of the bond enthalpies for the reactants, specifically the reactant bonds broken, minus the sum of all of the bond enthalpies for the products, specifically for the bonds, new bonds formed. Okay? Notice the order of this. It is reactants minus products. This is the first time I have given you an equation that does not have the final in the first position minus the initial. Notice how it is reversed. It is reversed from the final minus initial. This is the only time I've given you an equation like this, where it's reactants minus products. Initial bonds minus final bonds. Okay? So be very careful about that. That is the source of a major mistake that students make on this specific problem. On Other types of enthalpy calculations, it's final minus initial. But on this one, reactants minus products, okay? All right. With that in mind, we're going to do a sample problem here. Well, in this problem, I've been very nice to you. I've said using the values for the bond enthalpies. So we know we're going to use the bond enthalpy method. But another way that I could have worded this problem that would have been a little bit more subtle is I could have said, starting right here, calculate the delta H for this reaction for the following chemical reaction using the following information. And then I could have given you a list of some of the bond enthalpies. And you would have had to recognize, aha, I'm being given bond enthalpies, so I'm going to use the bond enthalpy method, right? Well, first, and this is very important, we have to have a balanced chemical reaction. Because if I have more than one of these molecules that are reacting, then I have to consider all of the bonds in all of those molecules that may be broken. So let's quickly balance this. 1 carbon, 4 hydrogens, 4 hydrogens, 2 oxygens, 1, 2, 3, 4 oxygens. There we go. Now we have a balanced chemical reaction. So after we have a balanced chemical reaction, the next step is we're going to draw Lewis structures. When we draw the Lewis structures, that will show us the kinds of bonds that we have in these molecules. And we'll then be able to see which ones are broken and which new ones are formed. Now, I'm not going to go through the whole process of how you draw these Lewis structures. You can go look at those videos and that material in a previous chapter if you'd like to do that. I believe it's in our chapter 4 or 5, depending on the version of the lecture workbook that you have. For now, I'm just going to go ahead and draw the Lewis structures because I happen to know what they are. And if you have more than one of these molecules, I want you to draw out the Lewis structure multiple times as a reminder that, hey, we've got more than one molecule to consider. So for CH4, methane gas, here's our Lewis structure. Pretty simple. We have 4 CH bonds, and now I'm going to write that down below here. I have 4 carbon-hydrogen bonds. When we do O2 gas, the Lewis structure is like this. And I have 2 of them. So I'm going to draw them both, right? And I have a total of 2 oxygen-oxygen double bonds. That's my reagents. And my products, I have a carbon dioxide. So if they do the Lewis structure, it looks like that. I only have 1 carbon dioxide, but that gives me 2 carbon-oxygen double bonds. For water, I have 2 of those molecules. I'm going to draw them both. And notice now that I have 1, 2, 3, 4 of these oxygen-hydrogen single bonds. Okay? So that's the next step, is to draw the Lewis structures for everything that you have, determine how many of which kind of bonds you have in the species. You may need to add more types of bonds if there are more things in here. For example, if this had an OH bond, I would write down 1 OH bond right here, but it doesn't in this case. Okay? So, now what am I going to do? Now what I need to do is I need to identify reagent bonds that were broken. And I'm going to use a red marker for this so that you can see that we're breaking bonds. So which of these bonds were broken? And that is to say, they no longer appear on the product side. We know that the bonds must have been broken if they don't appear in our products. In this case, we had 4 carbon-hydrogen single bonds. Do we see any of them over here? No. So we must have broken all 4 of those. And I'm going to signify that I've broken a bond by a squiggly line through the bond. So it's obvious that I broke all 4 of those. So I broke 4 carbon-hydrogen single bonds. Okay? Making a note. What about this reagent? Which of these bonds, if any, were broken? Well, I had 2 oxygen-oxygen double bonds. Do I find any of them over here? No. So it appears that both of those must have been broken. So I signify that, showing my work, really, my thinking. I must have broken both of those bonds. So I broke 2 oxygen-oxygen double bonds. I've dealt with all my reagents. Now I look at my products. In my products, I'm going to be identifying the bonds that were newly formed. That is, they did not appear in my reagents, so they must have been newly formed. Well, in this product, I have 2 carbon-oxygen double bonds, and neither of those appeared in my reagents, so it looks like both of these are newly formed. And for this video, I'm going to use green and just point a little arrow to say, hey, I want your attention here, because look, these are new bonds. So new bonds, 2 carbon-oxygen double bonds, right? See how am I distinguishing between breaking a bond and pointing out that a new one is formed? The squiggly line breaking the bond, and the arrow pointing to something that has newly appeared. H2O, I have 4 OH single bonds. Did any of them occur in the reagents? No. So they must all be new. So I'll go ahead and indicate all of them as new. 1 there, 1 there, 1 there, and 1 there. So I have 4 new bonds, OH single bonds. It just so happens that in this example, all of the reagent bonds were broken, and all of the product bonds were newly formed. But that doesn't always happen. In some reactions, you might only have 1 bond that is broken, and all of the rest stay intact because they can be seen on the product side, right? So then you would only put that 1 bond down. Similarly, on the product side, you may only have 1 or 2 bonds that were newly formed, and all of the rest of the bonds that are in the products were already there in the reagents. So you would only mark down the ones that you had newly formed. Now we are done with this part of our assessment, or of our analysis. Now we get to our equation. We know that the delta H for this reaction equals the sum of the bond enthalpies for the reactants, bonds broken, bonds, B-O-N-D-S, broken, minus the sum of the bond enthalpies for the product, bonds formed. Okay, the B-O-N-D-S, okay. All right, so now I'm just going to start plugging in. I'm going to put my reactants in brackets so I don't lose track of where that subtraction sign goes. And then my products in brackets as well. So the bond enthalpies for my reactant bonds broken. Well, I need the bond enthalpies. Actually, let me say 4 times, because I need 4 of them, don't I? 4 times the bond enthalpy for the CH single bond plus, remember the sum of the reactants, 2 of these of the bond enthalpies for the oxygen-oxygen double bond, On the product side, I have 2 of the bond enthalpies for the carbon-oxygen. And notice specifically, this is that special case in CO2. So I'm going to make that note so I don't forget, because that's a special case that we have listed. Now I'm going to continue my summing of my product bonds that are newly formed, 4 of the bond enthalpies for the oxygen-hydrogen bond. Okay? Again, initial minus final. It's the only equation I've given you for a delta in which you calculate the delta by an initial minus final. All other delta calculations that we've worked with are always final minus initial. So with this and this chart with the bond enthalpies, I'll leave it on the screen so you can make a note there. You can come back to it. With this data and the equation as I've set it up for you, I want you to go ahead and plug in the appropriate values, get an answer, pause the video, go ahead and finish this work, and give me the answer for this. And when you're done, resume the video, and I will come back and finish it. All right, resuming the video, we're going to start plugging in these values now that we know how to arrange them. So, 4 times the bond enthalpy for a carbon-hydrogen single bond, which is right here, 414 kilojoules per mole. So it's 4 times 414 kilojoules per mole, plus 2 times the bond enthalpy for the oxygen-oxygen double bond, 498.7. kilojoules per mole. That's all the reactant bonds that have been broken that we had to put heat into, right, to get these bonds to break. Minus the energy that we're going to get back by forming new product bonds. So that's 2 times the bond enthalpies of the CO double bond, specifically in CO2. There's our specific example there, 799 kilojoules per mole, plus 4 times the bond enthalpy for the OH single bond, 460 kilojoules per mole. Okay, so you can see how I'm setting up my work. Now I'm going to continue on to do the math. I'm going to simplify these. I'm not going to do all this all in one step, because if you do this and you had an error in your calculator, I want you to be able to track the math that I'm doing so that you can find out where you may have made a mistake. And you can see I'm going to get a negative number, right? Because this subtraction is going to be larger than that. So what does this mean? This means that it required this much energy to input per mole to break the reactant bonds. And then when the product bonds, the new bonds formed, it released energy in this amount. So that overall, it released more energy than I had to put into it. And that means that overall, the reaction released energy. And if it released energy, it's exothermic, which we certainly would expect that for a hydrocarbon burning, right? This is a combustion reaction, and we know that they give off heat. So methane gives off heat. And that's methane that we use in our Bunsen burners, right? So we know it gives off heat. So our answer should have been negative. And so here we're going to do this last step. And so we get a negative 784.6, and I'm going to round, since this is addition subtraction, I'll round to the nearest ones column, since this number is not precise out to the tenths column. Okay, so this would be negative 785, and this is kilojoules per mole. And that is the delta H naught for the reaction, right? Okay, a couple of issues that I want to raise with you about the bond enthalpy method. Look at all this. Look at everything that we had to do in order to calculate the delta H naught of a reaction using this method. It's relatively more involved than if you just were given the standard enthalpies of formation, for example, or followed a Hess's law. However, that's not the main issue. That's not the main reason that we tend not to use this. Really, the main reason that this is not as useful as the other methods for calculating a delta H is because these values that we have for the bond enthalpies for these bonds, these values right here, they're based on averages. And so they're always a little bit inaccurate for any particular specific case that you're looking at. We teach this method, though, because it does teach you a very important concept about chemical reactions. And that is, when you break bonds, it requires an input of energy. And when you form new bonds, they become more stable species, so it releases energy.